If you have built one AI agent and called it done, you're probably a lot behind. Single agent systems aren't going away, but they have quietly become the step one, not the finish line. Every serious production system I'm seeing right now is moving towards multiple agents and not just a single one. So there are multiple specialized agents working together, and it's not that a single agent is doing everything. A support agent that hands off to a billing agent, a research agent that spins up three sub agents to investigate in parallel, an incident response setup where agents debate and converge on a root cause without anyone directing them. That's not a future trend. That's how AI systems are getting built on 2026. But here's nobody tells you when you start building with multiple agents. The moment you have more than one, you have to make an architecture decision. Do they run in fixed order at the same time? Does one agent direct the others, or do they all talk to each other freely? Get this wrong, and you will end up building something very slower, expensive, and even worse than the single agent you had built earlier. Now, there's a handful of design patterns, and I mean the agentic AI design patterns that answers exactly this. Each one solving a completely different version of how multiple agents actually work together. If you're building anything with AI agents right now, this is the one that you do not want to skip. For each pattern, I set up the real situation, guess the pattern with you, and then show you how it actually works. Let's begin with the first scenario. You're building your very first agent. A customer asks about their order, and answering means checking a database and calling a shipping API. So there are two tools and one request. Nothing more complicated than that. So what do you reach for? This is the single agent pattern. One model, one system prompt, and a defined tool set, deciding for itself which tool to use and when. As you can see, the customer is questioning where is my order, so and so. And then the agent tries to understand the request and decide which tool to use in order to, answer the questions regarding that order. And then the same agent is trying to fetch the order details, the status, the items, etc. from the database, followed by getting the latest tracking updates and an estimated time of delivery. And once it receives all the answers from various sources, it then responds back to the user with the respective or corresponding answer. So, as you can see, there is one model, one system prompt, and a defined tool set. So, the model itself decides which tool to call and in what order based on the request. Now, the benefit of using a single agent pattern is basically, it's definitely the right place to start any agent project, and you can build and refine your core logic here before reaching for anything more complex. However, as you add more tools and responsibilities, tool selection gets less reliable and latency creeps up. Then that's is actually your signal to consider spilling into multi-agent systems. Moving on to the second scenario. So let's say you are from the content team and you are trying to build a content pipeline. So a draft needs to get written, and then the facts need to get verified and checked, and then optimized for SEO, search engine optimization, followed by the formatting for the CMS. So as you can see, it has to follow an exact order every single time and without any variation. So what do you reach for? Here comes the sequential pattern. So, a sequential pattern is a fixed chain of specialized agents that runs in a predefined linear order. So, as you can see, the AI writes the initial draft and then it tries to verify the facts and sources, followed by optimizing the model response for more keywords, meta, and readability, and then formatting and preparing for CMS publish. So, a fixed chain of specialized agents runs in order. No model is needed to decide what happens next, since the sequence is hard coded. The benefit here is It's definitely fast and cheap, and since there is no orchestration overhead. However, this pattern is rigid since it cannot skip a step or reroute if something upstream changes, and one slow step delays everything after it. Moving on to the next scenario, which is the scenario 3. Let's say you're from the hiring team or the recruitment team, and you need to score a single job candidate on three completely independent things: skills match, years of experience, portfolio quality. And doing them one after another is wasting time you do not have to waste. So, what do you reach for? Here comes the parallel pattern: multiple subagents that run at the same time and get merged into one result. So, how it works? So, as you can see, here is a job candidate, and there are three parallel subagents which are working together. One is for doing the skills match and evaluating the technical and the core skills. Then the second agent is basically assessing the total and relevant work experience of that particular candidate. And then there is the third agent, which is basically checking the portfolio quality by reviewing the projects and the impact and the quality of work. And based on the assessment of all these agents together, the entire AI is actually assigning a candidate score to the candidate. So as you can see, the multiple sub-agents, they're running simultaneously on the same input, and the final step merges their output into one result. So this kind of pattern is definitely much faster than running the checks in sequence. But the merge step has to reconcile results that might disagree, and running everything at once briefly spikes cost and resources used. Moving on to the fourth scenario, which is specifically for any kind of e commerce business, wherein, let's say, the requests can come in all shapes, wherein there can be one customer wanting a refund, someone wants an order status, someone has a technical problem, and you need something at the front door deciding in real time which specialist should handle each one. So, what do you reach for this kind of scenario? Here comes the coordinator pattern: a central agent that uses the model itself to route each request to the right specialist. So as you can see, there is one customer comes in and he is basically, asking for a refund. So there is this centralized router agent which is trying to understand the intent and routes the customer to the right specialist. So here in this case, it will be the refund specialist which handles all the refund request. And then there are two parallel customer who comes in, and the second customer is actually asking for the order status, wherein the third is actually complaining about a technical fault. So the router agent tries to understand their intent as well, and forward their request to the order specialist and the tech specialist, respectively. So a central agent is using the model to read the request, decide what kind of task it is, and hand it to the right specialized agent. The routing itself is a model decision and not a hard coded rule. So the benefit of this kind of pattern is that it is more adaptable than sequential or parallel since it handles varied input. However, as you can see, every request now costs at least two model calls: the coordinator's routing decision plus the specialist's work. Moving on to the fifth scenario, wherein, let's say, you're from the platform team or you're from the IT tech team, and someone in your team has asked your system to put together a competitive analysis of three cloud providers, let's say AWS, Azure, GCP, anything. And that's not one task. It's research, then comparison, then writing. And the research part alone might need to split into one subtask per competitor. So, what do you reach for? Here comes the hierarchical task decomposition pattern. So this is a variant of the coordinator pattern wherein the decomposition can cascade through multiple layers. So as you can see, the user request for competitive, analysis of all the cloud providers, and there we have three layers. So layer one, which is basically breaking the goal into high level steps, and in this case, the steps will be researching, followed by the comparison between the cloud providers, and then writing the analysis report. Layer 2 will be the decompose, wherein it decomposes the research step into competitor wise subtasks. So it is first researching about AWS, and then researching about the Microsoft Azure, followed by researching about Google Cloud. And then the layer 3, that is the execution layer, wherein it executes all the tasks and completes the result of the chain, and it does a side by side comparison, and then writing finally the structured analysis report. And all the layers finally give a combined output of the comprehensive analysis. So as you can see, a top level agent is splitting the goal into subtasks and hands them to specialized agents below it. This pattern handles genuinely ambiguous, multi-layered problems very well. However, every layer of decomposition is more model calls, due to which cost and latency increases definitely. And a debugging of 5 layer agent tree is a lot harder than debugging a single one. Moving on to our sixth scenario, wherein nobody has the full picture. So let's say you are in the middle of an incident, and there is a logs agent, there is a metrics agent, and there is a run book agent also. And all of the agents have partial clues, and no single one of them has the full picture. So they need to talk directly to each other, definitely, and not report of through you. So what do you reach for this kind of scenario? So here comes the swarm pattern. So all to all communication between the agents with no central controller is the specialty of this kind of patterns. So every agent can talk to every other agent, and there is no central controller. You know, a dispatcher just gets the conversation started and relays the final answers back to the users. And you have to define your own exit condition, since nothing else will stop it. So the benefit of using this kind of pattern is, so it can produce genuinely creative and well debated results that a rigid hierarchy wouldn't reach. However, it's the most expensive and least predictable pattern on this list. With no central control and a poorly defined exit condition means agents can loop indefinitely without ever converging. Moving on to our seventh scenario. So let's say you just kicked off a deployment, and so now you need something to keep checking the health endpoint every 30 seconds until it comes back healthy, or give up after a fixed number of tries. What do you reach for? Here comes the loop pattern, wherein there will be a sequence that reruns automatically until an exit condition is met. So deployment is started, and then it checks for the health. If the endpoint is not healthy, it keeps on checking again and again and again. And between each checks, it will wait for 30 seconds. If the maximum number of retries are reached, it will give up, and it will shut down the system. Else, if it finds that the endpoint is healthy, it will basically give a success response, and it will continue with its next task. So a fixed sequence of sub agents, rerunning automatically, checking an exit condition, maximum number of iterations, or a specific state after each pass. So it can keep checking at fixed intervals, stop whenever the system is healthy, or after maximum amount of retries. So you can see, like, it is simple and reliable. However, the failure mode here is specific and dangerous. So if the exit condition is written wrong, or the thing you are waiting on never resolves, you get an infinite loop which can burn your cost with nothing to show for it. So get the exit condition right before anything else, and it burns out your all your budget and pocket. Moving on to our eighth scenario. So an agent just wrote a database migration script. Before that script touches anything, you need something else to check for destructive operations and confirm it passes a dry run. What do you reach for? Here comes the review and critic pattern. So this is a variant of the loop pattern that we just discussed, and it has two distinct roles: a generator and a critic. A generator agent produces the work. A separate critic agent checks it against explicit criteria and can approve it, reject it, and send it back with specific feedback for another pass. So in this case, the script is generated and it submits the script for validation. And there's a validation gate that checks for whether the script has any kind of destructive operations or not. And it will do a dry run. If the basically if let's say if the checks are failed, it will ask for validation again. And then if the checks are passed, which means that there is no destructive operations identified, it will be marked as safe to proceed and the migration will be applied. So this kind of patterns can be used in, let's say, DevOps teams, or teams wherein which deals with databases migration, and a lot of things related to that. So the benefit is, it meaningly improves the reliability on anything high stakes. However, every pass through the critic is another model call, and a script that keeps failing review keeps costing you more, not less. So it means that the sooner the script passes, the lesser it will cost you. Moving on to our ninth scenario, wherein an agent drafts a Terraform config and runs the Terraform plan command, and then the plan comes back with errors. So you want it to rewrite the config based on those errors and keep trying until the plan is actually clean. So what do you reach for? So this is a scenario that is normally seen in the infrastructure teams, or let's say the cloud enablement or cloud engineering teams who are trying to provision the infrastructure for their various tenants. So here comes the iterative refinement pattern. So this is another variant of loop wherein one or more agents keep reworking the same stored result. So how it works? So let's say the agent generates the Terraform configuration, that is the main.tf files, and then it executes the plan stage of the Terraform by executing the Terraform plan command, and then it sees if there are any errors given by the Terraform SDK or not. If the plan is clean, well and good, it passes and it applies the changes to the infrastructure. It can be any resources of AWS or Azure or anything. However, if there are any errors in the plan, it will first parse the errors from the plan output, and then it will try to rewrite the configuration of that Terraform file to fix the issues. So you can see, right, one or more agents here are trying to keep modifying the same stored result across a loop, checking after each round whether it's hit a quality bar or a maximum number of iterations. So the benefit is that it can be the most reliable way to get a genuinely polished result out of an agent. However, you are paying in latency and cost for every extra round, and you need a real quality check, not just iterate three times, or the possibility that you will stop either too early or too late. Moving on to our 10th scenario. wherein let's say you're from the DevOps team, and let's say you have written a CI pipeline, and a CI pipeline is failing and you don't know why yet. So you need an agent that can reason about what might be wrong, run a diagnostic, read the result, and reason again. So not one that guesses once and stops. So what do you reach for this kind of scenario? Here comes the most popular pattern, which is the react pattern. React stands for reason and act, a thought, action, observation loop. So the agent cycles through the thought, what should I do next? Then it actions, call a tool based on that thought, and observation, read the result and fold it back into what it knows. So here you can see, like, the initial state is where the CI pipeline was failing, and it tries to think, it tries to reason about what can be the possible, reasons and possible causes behind the failure. And then it tries to action. So what it actions, it basically tries to run a diagnostic test, or some kind of commands to get the information of that pipeline. And then it tries to read and understand, it observes. So it reads and interprets the result from the logs, from the CI pipeline log, and then maybe the outputs or the metrics. And then it tries to think again, by based on the new information, and accordingly it will decide the next step. Until and unless the issue is resolved, it will keep on running the same procedure again, like think, action, observation, and then again think, action, observation, like that. So the benefit is, it is genuinely adaptive and it's thinking out loud. Transcript makes debugging easier due to that. However, each cycle adds a latency, and a bad tool, result early in the loop can send the whole chain of reasoning in the wrong direction. 11th scenario, wherein there's an agent which just drafted the exact SQL for a production database migration. So before it actually runs, you want a real engineer to look at it and approve it first, which means that you need a human to sit and validate. So whatever the agent response or whatever the SQL script is written, is it really correct and legit or not? Here comes the human in the loop pattern. So in the human in the loop pattern, there will be a checkpoint where the agent pauses and waits for a person before continuing. So in this kind of patterns, the agent runs normally until a predefined checkpoint, then pauses and calls out to an external system to wait for a person to approve, correct, or reject before it resumes. So in this case, it will be, let's say, the agent first drafts the SQL and it submits for review, and then a human comes in, let's say a real engineer or an SME or an expert, database expert, comes in to review the SQL written by that agent. And then the engineer tries to understand whether the whatever the agent has written is correct or not. If he finds that the script written by the agent is correct, so it he will either approve or request for changes to the script, and then accordingly the agent will execute the migration. So the benefit is that this is the pattern for anything where a mistake is expensive or irreversible, and a human in the loop can avoid those kind of mistakes made by the agent. However, it only works if you actually build the approval system it depends on. So that's the real infrastructure, not a checkbox. Last but not the least, scenario 12. Let's say a refund request comes in from the customer, and you as the, let's say, the support executive, you need to check the purchase and refund eligibility at the same time, whether the customer who is asking for the refund is he really eligible for a refund or not. And then depending what you find, you route to two totally different next steps. A processor, let's say a processing team, who will process the eligible refunds, and then a store credit flow for everyone else. So what do you reach for? So this is the custom logic pattern, your wherein your own orchestration, mixing patterns and rules where nothing off the shelf fits. So as you can see, the customer requests a refund, and then parallel checks happens at the same time. Basically, first let's say checking the purchase, wherein the purchase really exists or not, and the amount, the status, everything, and then it tries to check for the refund eligibility. It tries to validate the policy, the time frame window. Let's say the customer have ordered way back, let's say 5 months back, and he has just come in and asking for a refund. So in that case, it doesn't make sense, right? So and then based on that, it will take a decision whether the refund is really eligible or not. If it is eligible, it will forward the request to the refund processor. If it is not eligible, it will store the credit flow. So how it works, so you write the orchestration yourself, conditional branches, mixed parallel and sequential steps. So as you can see, it's kind of a mixture of parallel pattern as well as sequential pattern, whatever the actual business logic requires. And instead of adopting one predefined pattern wholesale, you are just doing a mixture of everything. The benefit of using this kind of pattern is it is actually giving you most of the controls. However, you have to own all of it. So every branch, every edge case, every failure mode is yours to design, build, and debug, with none of the guardrails a standard pattern gives you for free. 12 patterns. And if you're trying to memorize all the 12 patterns right now, then you're doing this wrong. Here's the actual takeaway: you don't pick a pattern because it sounds impressive. You pick it by answering four questions. Is this task fixed, or does it need to figure out its own steps? Does it need to be fast, or can it be thorough? Can you afford multiple model calls? And does a human need to sign off before anything happens? Answer those honestly, and the pattern basically picks itself. That's the real skill here. Not the names, but the diagnosis. Sequential and parallel when the steps are already known. Single agent when you're just starting out. Coordinator, hierarchical, and swarm when the system has to figure out itself. Loop, review and critique, iterative refinement pattern, and react when the answer needs to get through another round of pass. Human in the loop and custom logic pattern when the stakes or the shape of the problem doesn't fit into specific standard. And going back to what I said at the start of all this, single agent isn't dead. It's still where you should start every single time. But the moment your system needs more than one agent, the pattern you choose is the difference between something that scales cleanly and something that quietly burns money in circles. If this was useful, like this video, share it with someone who's building agents, and subscribe to the Techie Chef for more.